Bismillahirrahmanirrahim. In this lab, we will study the implementation, the logic of different type of the adders. As we can see in examples, here in example 1, we will study the Verilog code for an unsigned 8-bit adder. Here is a Verilog code for the 8-bit adder. We can see that A, B, and the output are the 8-bit numbers, and here we assign the sum is equal to A plus B. Now we simply copy this and go to the Verilog HDL file for the verification. Here is the same code, and we have to change the file name here, which is the exercise example 1. A, B are the inputs and sum is the output. 0 to 7 and all are the 8-bit numbers. Now we simulate this. It takes some time to compile. Now we can see here the full compilation was successful. We can locate the RTL view from here. Here is the RTL view of this. A, B are the simple 8-bit inputs, and here is a 8-bit adder which add the A and A plus B, and it show the output which is also the 8-bit. Now we verify it through the waveform. We insert the node here, node finder, list it here, copy this, and OK. Here we can see that A, B are the two inputs and sum is output. We set the 1, A is equal to 1 0 1 0 1 0 and 1 0, and B is equal to 0 1 0 1 0 1 and 0 1. Now we run the simulation. It also takes some time to compile. Here is the output of this. We can see this 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, 0 plus 1 is equal to 1, and similarly here the output is equal to 1 1 1 1 and 1 1 1 1. Now we go to the next example. Here in the example number 2, we have to write the Verilog code for an 8-bit unsigned adder with carry in, and in example 3 we will do this with the carry out. For this we simply copy this and modify this code according to our requirement. We copy this and go to the Verilog file here and copy here. Here we have to use the only carry in, not the carry out here, so we neglect the carry out, and here is the input carry in and input A, B, and third input is carry in. Here we neglect the carry out. Similarly from here. Now we run the simulation. It takes some time to compile. Here we have to change the file name, which is equal to exercise 2. Now we simulate this again. can see this time the compilation was running. We can see that the full compilation was successful. We can locate the RTL view from here. Locate the RTL view. Here is the RTL view. A, B are the two inputs, and here is a carry in, and here is a 2 adder, 8-bit adder, and here it shows the output 8-bit output. Sum is equal to now we go to the Verilog University Program VWF, and we insert the node here. Here we node finder, list it here, copy this, and OK. Here we have the 3 inputs, A, B, and carry in. Let's think for carry in is equal to 1, A is equal to 1 0 1 0 1 0 1 0, and B is equal to 0 0 0 0 and 1 1 1 and 1, which is equal to 15. Now we run this simulation here. This also takes some time to compile. Here it shows the output, which is equal to, we can see this as 1 plus 0 is equal to 0, 1 plus 1 plus 0. Here is a carry in 1. 1 plus 1 is equal to 0, and here is a 0 with the carry in 1, and here is a 1 plus 1 is equal to 0, and 0 plus 1 is equal to 1. And similarly at the next stage, 0 plus 1 is equal to 1, and 1 plus 1 is equal to 0, and here is a carry. 1 plus 1 is equal to 0, 0 plus 1 is equal to 1, and 1 plus 1, 0 plus 1 is equal to 1 here. Similarly at the next stage, here is a sum output, 8-bit output. For this we also converted this into the octal unsigned decimal. Here is a 170, here is a 15, and here unsigned decimal 186. Here is a 1. 117 plus 15 plus 1 is equal to 186. That's all for this carry in. And now we go to the, we perform the example 3, similar code for the carry out. Additional is with carry out. Here we neglect the carry in and we add the carry out here. Now in example 4, we perform this by using carry in and carry out both. Here for the carry out, we simply copy this and go to the Verilog HDL and copy paste it here and change the name example 3 here, and we have to neglect the carry in here. So here we neglect the carry in, so we remove the input carry in from here, and here from carry in we remove the carry in from here. So here is a input A and B are the two inputs, and here is the two outputs, sum and the carry out. y, and here we assign the a plus b, and sum is equal to 8-bit this, and the carry out is equal to 8-bit number. Now we run the simulation here. You can see the simulation is running. It takes some time. Here we can see that the full compilation was successful. Here we can locate the RTL view from here. Here is our RTL view. We can see that here the two inputs A and B, and here is the two output carry out and sum, and here is the 8-bit adder. Now we go to the university program VWF. Here we insert the node finder, list it here, and okay. Here we can see that here is two input and two outputs. Now we set the value of A. We convert it into the unsigned decimal. Now we set the value of A. From here, let the value is 148, and the here value is 88. Now we run the simulation here. Now here it shows the results. Here we can see that we convert also into the unsigned decimal. Here result is equal to 236. 148 plus 88 is equal to 236, and the carry out is equal to 0 here. Now we move to the next example. Here is example 4. In the example 4, we have to write the Verilog code for an unsigned 8-bit with the both carry in and carry out. Here is the both in this we have the both carry in and carry out. Now for this we simply copy this here from here and go to the Verilog file and paste it here. Here is A, B, A and C. These are the variable declaration, and here carry in A and B are the inputs, and output sum and carry out are the two outputs. Now we run the simulation. We have to change the file name here also, which is equal to x4. It shows error. Now we simulate this again. This time we can see that it is analysis and is run successfully. You can see that the full compilation was successful here, and we can locate the RTL view from here. Here is the RTL view of 8-bit adder. A, B are the two inputs, and here is a carry in input, and these are the 8-bit adders, and here carry out and the sum are the two outputs. Now we go to the university program VWF. Here we insert the node and node finder. Here list it, copy this and OK. Here is a 3 inputs and 2 outputs with a carry in and carry out. Now we set the values of A and B. We set the values here 1 0 1 0, and B is equal to 15, which is equal to 0 0 0 0 and 1 1. And 1. Now we run the simulation. Here it shows the output in the carry in and carry out. Both carry in and carry out are the 0. Here is equal to 0, 1 is equal to 1, 1 plus 1 is equal to 0 with the carry, 1 plus 1 is equal to 0 with the carry, 1 plus 1 is equal to 0, and 0 plus 1 is equal to 1, and 0 plus 0, here is a carry, and 1 plus 0 is equal to 1, and 1 plus 0 is equal to 1, 1 plus 0 is equal to 1 here, and 0 plus 0 is 0, and 1 plus 0 is equal to 0. Now we can run it from one another way. We set the value of B is equal to 1 here. Now we run the simulation again. Now we can see it from here. Here is it shows the carry out is equal to 1 because of here it shows the carry out 1. 0 plus 1 is equal to 1, 1 plus 1 is equal to 0 and with carry, 1 plus 1 is equal to 0 with carry, and 1 plus 1 is equal to 0 with carry 1, and 1 plus 1 is equal to 0 plus 1 is equal to 1 here, and with the carry 1, and 1 plus 0 is equal to 1, 1 0 plus 1 plus 0 1, 0 plus 0 0, 1 plus 1 is equal to 0 with carry 1, and it shows the carry because it is a 8-bit number. We cannot write the 9th bit here, and it shows the carry out, the 9th bit in the carry out. So it shows the carry out is equal to 1. So that's all for this example. Now we move to the next example. Here is example 5. In this example 5 we have to write a Verilog code for a 8-bit unsigned adder and subtractor for both. We can perform this for 8-bit adder. Now here we can perform this for adder and subtractor both with a carry in and both out. Use a selection input to select the addition and subtractor. We can add the selective pin to perform the one operation at the time, addition or subtraction. For this we write the code in the Verilog HDL. Here is the code for this subtractor here, and we know that in Subtractor we use the borrow in the replacement of the carry out. Here is the module file name, and here we declare the variables. Here input A, B are the inputs, and we write the code for the 8-bit subtractor, and we run the simulation. We can see here the compilation was successful. Now we look at the RTL view from here. We can see that here is RTL view. Here is a subtractor, sign minus. Here is A, B are the inputs, and here is a borrow and the subtractor are the output. Now we go to we show adder here because in the IC, the one IC which is used for the adder and subtractor are the same. Here we use the selector pin which convert the addition and subtraction. Now we go to the university program EWF. Here we insert the node here, node finder, list it here, and okay. Here we can see A and B are the two inputs. Let A is equal to, we convert into the unsigned decimal. Let's suppose A is equal to 70 and B is equal to 30 here. Now we run the simulation here. Here it show the output with the borrow 0, and here we convert it into the unsigned decimal. From here we can see that 70 minus 40 is 70 minus 30 is equal to 40. It had no borrow. When the B output is greater than the A, then it shows the borrow here. So that's all for this example. Now we go to the next exercise. Here is the exercise. In this exercise we have to construct and implement the logic of the 4-bit arithmetic and logic unit. The ALU should contain at least 10 functions given below in this table. We have to randomly choose the 10 operations. Please clearly state the function that you will be using the Verilog code. For this we have to write the code in Verilog code. Here we write the Verilog code for this construction and implement the logic of 4-bit arithmetic unit and use the 10 function here. Here we declare the variable here. Inputs are the A, B and OP are the inputs, and output is equal to out. And these are the 4-bit input and output. Here we use the case to operate the 10 operations. Here we use the 10 operations using selected from the table given in the from this. We select the 10 and using case study. Here we end the case and the study. We run the simulation. We can see that the compilation was successful here. Now we can see the RTL view of this from here. Get RTL view. We can see that here is the RTL view. We set this. Here we can see that here is the RTL view of this. Here it performs the logic gates here and the multiplexer. Now we go to the program, university program VWF. Okay, here we insert the node here, node finder, list it here, and okay. Here A, B are the two inputs. Let A is equal to, we convert into the unsigned decimal. We simply convert it to unsigned. Here is the output and readings unsigned decimal here. Now we set the values. Let's suppose it is equal to 15, it is equal to 1111, and B is equal to 1010, which is equal to 10, and OP is equal to, let's suppose it is equal to 1. Now we run the study. It takes some time to compile. We can see that the output here, because operation here it performed the operation number 1 0 1 here. We can see that the operation number 1 is equal to A plus B. A plus B is equal to operation number 1 0 0 1 is equal to, here is operation 0 and 1 is equal to A minus B here. 0 0 0 1 is equal to A minus B. It perform the subtraction here, so 15 minus 10 is equal to 5. We perform this one more. We set this, it is equal to, go to the here and we select the 5 here and run the simulation again. Here will show the output of the operation 5, which is equal to 10. Now we go to the coding. Here 5 is equal to 0 1 2 3 4 and 5. Here is the XOR operation. It performs the XOR, which 15 XOR 10 is equal to 10. So that's all for this.